Welcome to Ask and Learn.
So it says a 6.62 kilogram wooden block is firmly attached to a very light horizontal spring. So in this case, we'll draw a figure of the situation first. So there is a block, and the mass of this is 6.62 kilograms. The force constant of the spring is given as 180 newtons per meter, and the block is compressed. So what happens is that, first of all, the block is compressed. So this is its initial position, and it is compressed. So this is 0, 0, and it is compressed to 5 centimeters. So this is 5 centimeters, and then released. So what it's saying is that and there is a friction in the scenario, and this is the equilibrium position. So the block executes simple harmonic motion, and what happens is that what they're saying is that it stretches 2.3 centimeters beyond the equilibrium position before stopping and turning back. So that is our question. So in this case, again, we'll use the conservation of energy with the non-conservative force acting on it. And we know that the force of friction is equals to mu k mg. All right, now the location 1 represents the block at the compressed location. So this is our location 1. Okay, and the location 2 represents the block at the maximum stressed position. So which means this is our location 2. And this is the equilibrium position, which is at 0, 0. So at this location, we have V1 is equals to 0, and the x1, the displacement is negative 0.05 meters because it is toward the left of our 0 level. And at this location, the block comes to rest, so V2 is equals to 0, and x2 is equals to 0.023 meters. So let's apply the conservation of energy. So we have the total energy E1 should be equals to total energy at E2, but this is not the case in this scenario because there is friction. So the energy at 1 should be equal to the energy at 2 plus some work done by the friction force. So energy at 1 is equals to half mv1 squared plus half k x1 squared, and energy at 2 is equals to half mv2 squared plus half k x2 squared plus the force of friction, and this is the displacement. So the net displacement is x2 minus x1. So now we just plug in the values in this equation. So as you can see that v1 is 0, so therefore we have 0 plus half k x1 squared plus so in fact it is just simply 0 plus half k x1 squared on the left hand side. There's nothing else. And on the right hand side we have the velocity, which is 0 again at this point, so this is 0 plus half kx2 squared plus mu kmg, as we have seen, is the force of friction times x2 minus x1. So we'll solve that on the next page. So writing this here, we get the equation. I'll write again half k x1 squared is equals to half k x2 squared plus mu k mg x2 minus x1. So now we need to find the value of mu k. is simple. By rearranging the terms, you get mu k is equals to k x1 squared minus x2 squared divided by 2 times mg x2 minus x1. All right, so in this equation, if we just plug in the values according to the equation, but this could be actually be simplified. We can actually write down the numerator as x negative x2 squared minus x1 squared. I've just multiplied the whole thing by negative and divided by 2 mg x2 minus x1. Now we know that a squared minus b squared is equals to a minus b x2 minus x1 and a plus b x2 plus x1 divided by 2 mg x2 minus x1, which actually cancels, and we are left over with this equation. So therefore we now plug in the values. Negative 180 times negative 0.05 plus 0.023, which is x2 plus x1, divided by 2 times the mass, which is 0.62 times 9.8. If you solve that, you will get 0.4 as the coefficient of friction.